as Jean said, Simen and I kind of like combined talks, and the first half of the talk we're going to focus on horizontal shear. I'll do that, and then I'll hand it over to Simen, who's going to focus more on vertical shear and turbulence. And we hope, if we have time, to have a bit of a discussion after.
Do you hold the microphone pretty closer?
Just good? Okay. Cool. So it doesn't take me any, and as people mentioned before, Fabrice sort of like asked us to do this in a bit of an educational way. It doesn't take much convincing. At least, oops, how do I get rid of this?
Yeah, I'm afraid that the online audience might not hear you if you don't bring the microphone closer. Just put it on your...
The online audience?
Yes. Yeah.
Though I mean how I got rid of this.
To hear you. Just keep the microphone close to you, put it on your ears if you attach it like the other speakers. So
Is this good?
yeah, keep it close. It's like as if you're singing.
Okay, my chin. Oh, how about I use the other mic? Is that better? No? Is it?
It's charging, so
Okay.
limited power on this, so you could use the one you're holding.
Sounds good. Anyways, this goes back to Luigi's review in 2012. We're now, all of us, are very aware that winds, currents, and waves form a coupled system. And this is rather a complicated and complex system that it's constantly interacting two ways. So instead of going about everything that's going on here, today I'm going to focus. It would be great if my slides moved.
Move the cursor on the image and then click. No, does it not do it?
It did it. All right, so I will focus only on wave-current interactions, but then this is still very broad. So a better title for this, it's actually, I'll be talking about some effects of surface currents on linear deep water waves. That means that this talk is not going to focus on how currents can affect wave breaking and other nonlinear processes, and we heard a little bit about this during Mark and Lionel's talk. As I said, Simen is going to talk to us about vertical shear right after me. Later this afternoon, Nick Pizzo is going to talk about how waves generate currents, so I'll also not be focusing on this arrow. We will hear later on a little bit about how currents can affect waves in the near shore later this week, so I'll also not focus on that. And I'm also not thinking about things such as relative wind, for example, or how currents may impact wave generation. Or, for most of the time, I'm also going to be focusing on currents that are stationary or steady-state type of solutions. So nothing like tidal currents or long wave, short wave interactions, for example. So just so we're all on the same page, although I'll move through these rather quickly, if we start from a geometrical optics framework, we can describe the kinematics of surface waves using ray equations, where here we see that currents come into play by introducing a Doppler shift in the dispersion relationship. We also see currents in the conservation of absolute frequency, and again for this talk, this term will mostly be zero because there is no time dependence in U. And then currents come into play, current gradients come into play by changing the direction of waves or refraction, and also by changing the wave number, or as Fabrice likes to call it, the concertina effect. And finally, currents can also change the speed at which wave action is advected. And since I mentioned action, although the kinematics of this system can be described by the ray equations, the dynamics are governed by the conservation of wave action, which is just the ratio between the energy and the intrinsic frequency. And this equation, it's written in a very wave model-like of way. And again, we see currents coming into play over here, changing the speed of action advection, over here through the changes in wave number, changes in direction, and of course, currents will also affect the source terms. And again, just for completeness, although it's not really the focus here, we got changes in the relative wind, so currents will come into play there. Currents can highly change the shape of the wave spectrum, and that will impact both braking and nonlinear interactions. All right, so the theory describing these processes, nothing of this is new, and the theory dates back to the 60s, where Longen-Higgins and Stewart brought this up using a radiation stress framework, whereas Bretherton and Garrett focused on wave action. But if we look at early observations of these processes, most of the observations focused on large-scale currents. So over here on the far right, we see the modulation of significant wave height by a tidal current observed by Vincent in '79. And if we focus on spatial variability of the sea state, part of the challenge here is that really there's no good way to measure that unless you're doing things from remote sensing platforms. So here's a classic example from MAP in '85, looking at wave refraction through the Gulf Stream, whereas here it's pretty cool actually. It's a bunch of directional spectra as the waves are crossing the Agulhas, and you see the intensification of the energy around the peak as observed by Ardhuin and Tiley. So part of the reason for why the earlier observations focus on large-scale currents is really like an observational challenge. So the question that arises is how wave properties vary at shorter scales or in the meso to sub-mesoscale range. So we're talking here now scales between hundreds of kilometers all the way down to about a kilometer. And then there's been a lot of progress in this direction back in 2017. There we go. Okay, so there's been a lot of progress in this direction, and one thing that is important to keep in mind is that the waves themselves, they vary on a broad range of scale. So a lot of people in this room have contributed to this problem by focusing on short waves or high spectral moments. For example, here's a figure from a paper by Nicola Husk, who did a lot of work looking at the mean square slope. Over here on the bottom, that's a map of the Stokes drift modulated by surface currents from a paper by Lionel. And then we have, here's a picture similar to what Lionel was trying to show. It didn't work out. And so here we see things that are a bit more localized. So how the wave field respond to like coherent features such as like fronts, both in this paper by Theodore and here on the bottom, paper by Nick and Luke. All right. There's been a lot of other people in this room, myself included, who have focused on lower moments, such as the significant wave height. Part of that is it's easier to observe these globally thanks to satellite altimetry. And throughout the remainder of this talk, I'm actually going to focus on significant wave height, right? And I'll just take some minutes to walk you through some of the things that we're looking at here. So back in 2017, Fabrice and collaborators published this paper where they looked at the response of the significant wave height to currents. And so here on the, I'll give you a minute to laugh. And so here on the right-hand side, we have the significant wave height from WaveWatch forced with ROMS currents in the Gulf Stream with currents, and on the right without currents. And there are two main key points from this paper. The first thing is that the wave number spectrum of significant wave height, and I know this is a weird concept for people who are not thinking about this, because it's not the wave spectrum, it's the spectrum of that map. It's the wave number spectrum of significant wave height. It seems to follow the spectrum of the kinetic energy or the current spectrum. And then Fabrice points out that refraction seems to be the main mechanism at larger scales, so let's say scales of hundreds of kilometers, whereas as you start to approach shorter scales, advection, it actually starts to win over refraction. And then Lionel went ahead and pushed this limit to much higher resolutions. So here we're looking at a figure that it's also WaveWatch forced with ROMS in the Santa Barbara channel. But now we're looking at currents that have resolution all the way down to hundreds of meters, not kilometers. And Lionel found something similar, that even at such short scales, the significant wave height seems to follow the spectrum of the kinetic energy. However, if you focus here, the blue is the kinetic energy spectrum, and you see that at very high wave numbers, the significant wave height actually decays faster than the kinetic energy. And we're gonna come back to this point later in the talk. All right, so this is all from a modeling point of view, but how about observations? Well, again, it's a bit tricky to observe these processes because you need to sample the wave field over a wide range of scales. But people have done a lot of progress using remote sensing observations. So here I'm showing some results that were led by folks at IFRAMER. And if you look at altimetry observations of significant wave height, it's actually pretty noisy, all the way down to hundreds of kilometers. So folks came up with a method, an empirical method called empirical mode decomposition, or EMD, to filter out this noise, and then you can actually start to see a little bit of the current signature in the wave field from altimetry, down to scales of about 50 to up to 30 kilometers, depending on where you are. And I think that is really striking that this paper from Kifan et al. Showed is how spatially, the wave gradients, so the significant wave height gradients, have a very good correlation spatially with where we have strong currents, right? So it's really, we all know now that that's the main driver for significant wave height gradients. All right, so things seem to agree, model results and observational results. But really the question is, like, what are the mechanisms at play here? Why are significant wave height responding this way, and what is the physics behind this? So in order to investigate this a bit further, I conducted back in 2020, together with Fabrice and my PhD advisors, a series of semi-idealized experiments. And I've talked about this a bunch, so I'm not gonna go over the details, but if you haven't seen this before, the gist of it is that we're looking at significant wave height on every single panel. And what I did is that I forced wave watch with different flavors of currents, where if you go from left to right, you start with currents that are very vertical, so they only have vorticity. And as you move down, you decrease the amount of vorticity until you get currents that are purely divergent. And then if you go from top to bottom, what I'm changing is the kinetic energy spectrum of the forcing of the currents. So on the top, I'm forcing the wave watch simulations with currents that have a shallow spectral slope for kinetic energy. And on the bottom, it's for steep spectral slope. So there are a couple of things that came up from these. I run an ensemble with a bunch of this, and there are a couple of things that came up from it. One thing is that, yes, the spatial variability of significant wave height seems to be mostly driven by the rotational component of the flow, which indicates refraction to be the main mechanism behind. You can see this really clearly when you see that the gradients, when you're forcing wave watch with vertical currents, are much stronger than when you're forcing them with divergent currents. The other thing that pops up that's really interesting is that the significant wave height response, it's highly anisotropic. You see these streaky-like features that are aligned with the direction of wave propagation. So in all the simulations, waves are propagating from the left boundary to the right boundary. So you see these streaky-like features, and most of the variance is in the across wave direction. And then finally, if you just focus on the first column, you see that there seems to be a scale dependence between where the variance of the currents are and where the significant wave height response is, meaning that on the top, where you have a shallow kinetic energy slope, meaning more energy at high wave numbers, your significant wave height has finer structures or gradients that are shorter scales when you compare it to the bottom, where you have these large scale blobs. All right, so this is all old news somewhat, But still, although the idealized simulations helped to build intuition on what's going on, we still lack a theoretical framework to really understand the physics at play here. And so now I'm going to switch gears and talk about some new results, and that is focusing on understanding the physics behind all of these numerical simulations. And this is work mostly led by Han Wang, who's a postdoc at the University of Edinburgh. And Han is working with myself, Jacques Van Est, and Bill Young at Scripps. The first part of this work came out in JFM last year, and we just got the reviews back for what I'm going to talk about today, but you can access the archive draft using this QR code here. So, what do? We have this thing called the U2H map, and U2H essentially maps the surface currents U to a significant wave height anomaly H, and it relies on a few assumptions. We need to assume that there is a scale separation between currents and waves. There are no sources of sinks of wave action, meaning our right-hand side is essentially 0. Again, we rely on a simple weak current assumption, and that's our small parameter, just U over C. And we also are looking at steady state solutions, so the wave field is passing through the currents as if the currents are frozen. The other thing that we need to assume is that the background action is spatially uniform, meaning that if there were no currents, your action would be the same all over in space. And then finally, that the perturbations that we're going to get in HS are small in comparison to this background value. I will walk you through the details of U2H in the next few minutes, but the gist of it is normally we take our currents, these are currents from the MIT GCM, you pass them through WaveWatch, and then after lots of CPU hours, you get something that looks like this. That's a significant wave height anomaly. And then what this framework offers is an opportunity to take the same currents, you pass it through U2H, and this is what you get, meaning that with just a few seconds, you can have a pretty good representation of the spatial variability of significant wave height with minimal cost. Okay, so we start from the conservation of wave action. We assume no sources of sinks. The next thing we do is that we expand this in our small parameter. And so we apply that to both our dispersion relationship and the action. And again, here, A bar is this background action. You see that it only depends on K, so there's no space dependence. It's all the same all over. And then we can go ahead and collect all of the order epsilon terms, which gives us this equation where you don't worry about mu here. It's just a dissipation to ensure that we have causality. And so if we focus on this equation, it becomes really clear that the perturbations in action lead away are linear in the current U. Okay. But we're interested in significant wave height, so we take HS and we can compute that from the action spectrum. But remember that we just expanded the action into this bar term in the perturbation. And so if you go ahead and do that, you then find that the significant wave height perturbation, the little HS, it's linear in the action perturbation. So we have this. But I just showed you a second ago that the action is linear in currents. Therefore, the changes in HS will also be linear in the current. And so we can take our HS and our wave action equations, and then we can solve them in Fourier space. And watch out here, because I introduced a new variable. K is just the wave number, so that it's related to frequency through the dispersion relationship, but Q, it's our spatial wave number. So it came from taking the FFT of something that has an X dependence. And so we have these two wave number vectors, where one is the wave number vector, and the other one is the spatial wave number vector. All right, and so if we solve this, it gives us this solution, which is the U2H map. So the Fourier transform of our HS perturbation It's related to the Fourier transform of our currents through this linear operator that is essentially a transfer function. And what I'm gonna do now, I'm gonna take the U2H map and try to come back to these statements and see what we can learn about these three results using U2H. So the first thing that, sorry, let me pause for a second. The first thing that we had from the numerical experiments is that we have these scale dependence between kinetic energy and significant wave height. And so why is that? Well, we start from U2H, but actually if you go ahead and you solve this operator, you see that L only depends on the wave number vector through its direction. So it's only a function of the angle. It doesn't depend on the magnitude of Q. And so this reduces to something that is just a completely linear relationship between the spectrum of HS and the spectrum of the kinetic energy. And so exactly the same shape that your kinetic energy spectrum has, that's going to be the same shape as your significant wave height. And so that particular point is proved. And then the next thing that we're claiming is that the variability of HS is driven by the rotational component of the flow. And then why is that? Well, we can take our velocities and decompose them into a rotational component associated with a stream function and a divergent component that came from a velocity potential. And then we can also decompose our operator. So now L_perp is a term multiplying the rotational component of the flow, and L_parallel is a term multiplying the divergent component of the flow. And if you have directional C states, meaning a small directional spread, then L_perp, it's much, much larger than L_parallel. Therefore, you would need the kinetic energy that is divergent to be a lot larger for this term to compensate for that. So this term always wins pretty much. And that's what we see. In my idealized simulations, actually the second to last column, it's an example where 80% of the kinetic energy is in the divergent component, and still you see that the spatial variability that you get, it's really streaky, being completely dominated by vorticity, although you just have a teeny tiny bit of vorticity there. This is not necessarily the case if you have a broad directional spreading, and I'll talk more about this in just a second. And if you remember the figure from the Romero paper, in the ocean, we have mostly balanced motions. I should probably point with this. So at large scales, we have mostly balanced motions that are in geostrophic balance and they're mostly rotational. But then when you start to get to high wave numbers, divergence kicks in and you get a flatter spectral slope in your kinetic energy. But your significant wave height is just going straight down because it's just following the spectral slope of the rotational kinetic energy. All right, and finally we have this anisotropy, which is really interesting. And to look at that, we note, and again, you can see the details in the paper just for the sake of time, but the variance in the cross wave direction divided by the variance in the along wave direction is proportional to the ratio between L_perp and L_parallel. And then remember, L_perp, it's always larger than L_parallel, and the minimum of this difference is 4. So the minimum that L_perp can be, it's 4 times larger than L_parallel, so it's always much larger, especially if you have narrow spreading. And here I'm showing an example where on the left, in the pink and blue, you have the kinetic energy spectrum of the forcing, and it's isotropic. But then when you look at the spectrum of significant wave height, you see that if you have a narrow direction spreading, the variance, it's all concentrated in the cross wave direction. And then as you increase your direction spectrum, your spectrum becomes a lot more isotropic. Okay, so this is a function of the direction spreading. All right, how am I doing on time? Okay, so just to wrap up U to H, we started off with action equation. We apply some magic asymptotic tricks. We find a linear map that takes you from currents to significant wave height. It works fairly well in comparison to wave watch for these cases where we have no source terms, okay? And you see that it works well if you have turbulence. So this is just currents from the MIT GCM, and it's wave watch and U2H. Also works if you have coherent structures. So the example there, it's the flow impinging on a Gaussian vortex. And you also see, and the rows are different direction spreadings. So you see that it still works pretty well for coherent features too. All right, but there's been a lot of assumptions that went into U2H, including no sources or sinks of action. Does it work, or is it any useful for the ocean? Well, it's a bit tricky to test until very recently. So I'm gonna show some brand new results, brand new as in like 2 days ago, that Gwen Marshall, who's a postdoc in my group, put together. And that's work in collaboration of Luc Lené, Alejandro Bôas, and Han Wang. And Fabrice has helped a lot with getting the data. For those who are not familiar with SWOT, SWOT maps the 2D sea surface height using these two parallel 50-kilometer wide swaths. And so it gives us a 2D picture of the sea surface height, SSH. And the goal of SWOT was to focus on sea surface height measurements. One thing that's pretty cool about SWOT is that the calibration and validation phase of SWOT, which is shown here, the site is shown here in this diamond, it overlaps in time and space with a very big field campaign, S mode, that you hear more about it in Gwen's talk later today. And so this means that we had all sorts of cool data, both from airborne data and in situ observations during this particular time, and I'm going to be showing you some examples from that particular period when SWOT was during this Calval phase. Okay, so the focus was on sea surface height, but surprise, surprise, SWOT see actual waves. You can see long swells in groups. Fabrice has a poster about this outside, and I believe you're going to hear more about it in Alejandro's talk as well, and Gwen will talk about this later today. So here, it's a snapshot of raw SWOT data, and if you zoom in this 2-kilometer box, the blues and greens that you see are actually crests of surface waves. And the other thing is that thanks to the algorithm developed at Cargèse, we can map not only the sea surface height, which is shown here, but also the significant wave height in 2D. And here's a comparison during Calval. It's a figure from Luc Lené. It's a comparison of SWOT sea surface height on the left, and the dots that you see are the LiDAR observations as the mass LiDAR was overflying the same track as SWOT. And the same with significant wave height. So it's the first time ever that we have access to these 2D images of significant wave height. So I'm showing to you an example of SWOT significant wave height. Again, this is data from Alejandro that was taken at that particular location. And the purple line shows the direction spectra from CFOSAT, from SWIM, in a day where we had a swell. Waves were about 200 meters wavelength. Significant wave height was close to 4 meters. And the waves are coming from the northwest. And the first thing that you see, and I'm not sure how good you see it in the projector, but is that you have these streak-like features that are aligned with the direction of wave propagation, confirming that the significant wave height response is highly anisotropic. And another indication of this particular behavior can be seen from if you just take SWOT currents, and now if you run ray tracing over them, you just see that the regions of convergences and divergences of action coincide with the highs and lows for the significant wave height. So this is a pretty neat example because the tracks, it's aligning in the swell direction. It's aligning in a way that allows us to do that. All right, now we're gonna take the currents from SWAT. So this is geostrophic currents from SWAT, and they're pretty crude still. And we're gonna use that to input into U2H and look at the U2H response. And then that's what you got, which I know I'm biased, but I feel optimistic about this. You see we have a low here. First of all, you see the same type of anisotropy, and then you see low, high, and then a bunch of lows, and then you have this high, and then this high, and then a bunch of lows, and then a high and a high. And part of that, U2H doesn't consider any sources and sinks. But the other thing too is that U2H can just be as good as the currents that you feed to it. SWAT is seeing the significant wave height as it is, but U2H is seeing the significant wave height from the geostrophic currents from SWAT that you pass on. So that could also be an indication of the uncertainty in the currents themselves and the fact that we're not capturing all of the currents because it's just a geostrophic currents and there is also a limitation in the resolution. I'm sorry, what?
It's also just in the SWAT.
Exactly, and it's also just in the SWAT. Which we have another SWAT that we can look at too, right? So this is literally like 2 days ago. So I feel that, there's another thing. U2H needs the incident wave spectrum, and we use that CFO spectrum that I showed, which also we saw that everything is really sensitive to the direction of spreading. So if you get that wrong, that can also change a lot the results. So we're gonna continue to look into this. I blurred this out here because you can also take the currents and pass it to WaveWatch. And usually U2H and WaveWatch agree very well, and I don't understand what's going on here, so I'm not gonna talk about it. But we will figure it out. All right, I think my time is probably up. And the last thing I wanted to do is to just wrap up and leave some key points in terms of things that we know and things that we don't know. So what we do know pretty well from work from everyone, pretty much a bunch of people in this room, and from the things that I showed today, is that currents can lead to very strong spatial variability in the wave field. And I focus on HS, but again, keep in mind that many others here have focused on the higher moments, and they're also very important. Refraction almost always wins just because of the way how the ocean works. The kinetic energy spectrum in the ocean is red, and you would need the divergence to be really strong for that factor to actually matter when we do the decomposition. The wave response is really dependent on the direction of spreading. And this is really interesting, because usually swell has a small sigma theta, and Cs have a large sigma theta, but this is not sensitive to the frequency or to the bandwidth of the spectrum. It's just, so we tend to think that short waves will respond differently than long waves, but what's governing here is actually the direction of spreading, not the frequency. I would like everyone to keep in mind that refraction is very much non-local. So when you're thinking, I'll come back to this in a second. And U2H was developed based on the action spectrum, which means that if we start from the point before we computed HS, we can use that same framework for other moments. So we could have a U to U Stokes map as well. All right. No source terms. From swell. Stokes from swell. A lot of this stuff remains unobserved, and this might change now with S mode and SWAT, but it's still. And the two food for thoughts here are, how does this state gradients feedback into the couple or system? Like, we have relatively small scale gradients. Is that going to have a net effect on large or climate scales? And should we be thinking about these spatial gradients when we're thinking about parameterizations that are wave aware? All right, so that's it for horizontal shear. I'll pass it over to Simen, I hope.